Now that we've looked at how to create a confidence interval for a estimation of a population mean, we're going to do the same thing now, but under a more realistic scenario when we're not sure about the standard deviation or the sigma of a given population. We're also going to look at a formula that helps us determine ahead of time how big we should make our samples in order to get a result that is within a certain level of confidence and a given margin of error. We're first going to look at the sample size formula. Margin of error is actually tied inversely to the size of our sample and directly to the level of confidence that we are after. In setting up a study, it's important that we, ahead of time, know how big our sample should be so that it fits the outcomes we desire. Usually we're not going to want a very large margin of error because it doesn't hone in too closely to the desired population parameter that we're trying to estimate. So we want to make sure the margin of error isn't too big, and we want to have a high level of confidence that our interval contains the population parameter we're after. So it's really important for us ahead of time to figure out how big of a sample we should shoot for. If we take the margin of error formula and solve it for n, we get this. And this is the formula that solves for n, where n is the sample size that we're after. Z is the given level of confidence, it's the Z value associated with the level of confidence we want for the desired margin of error. In a particular population, the sigma will be decided ahead of time. If we don't know the population standard deviation, we can substitute the sample standard deviation, which is given by the letter S. Whenever we're talking about a standard deviation from a sample, we use S as the symbol for it. Or we can use the standard deviation from a previous study and just assume that that is the population standard deviation. Regardless, this gives us an idea of how big of a sample we should get as we're looking to do our study. So here's an example. We are trying to figure out what is the minimal sample size needed if we want to be 95% confident that the sample mean is within 1.5 units of the population mean. An estimate for the population standard deviation is 8.4, and it's available from previous studies. So in this case, we're told that the margin of error is 1.5. This is not 1.5%, it's 1.5 units of our population mean. The level of confidence is 95, so we know that the critical value we want to use is 1.96. And our standard deviation was given as being 8.4. Using our formula, we simply plug these values in. Notice this is a Z value for the given level of confidence, not 0.95. And then we put our standard deviation and our given margin of error, and we square that product and quotient. This gives us 120.47. So if we're looking to collect a sample, obviously we cannot collect half of a sample here. And so even though this result is below 5, and we would normally round down to 120, if we round down, we may end up risking not having the desired level of confidence and the desired margin of error we're after. And so for this result, given that it's an n and it needs to be a whole number, we simply always round up. And that will give us the minimal sample size that we would need in order to make to get a sample that will have this margin of error with this level of confidence. Now let's take a look at how we estimate population means via confidence intervals when we don't know the sigma about our population. So our assumptions for our studies have changed in this section. However, number one, we're always going to assume that the sample that we do get is a good sample and that we derived it from a simple random sample, and that the distribution of my population is approximately normal. That means that's my original data, that it's got an approximate normal distribution. We also don't know the standard deviation of the population. This, of course, is the most important part that signifies that we need to use this method as opposed to the z-table, which we did in the previous section. Given the above scenario, we have to revise our formula for calculating error. And here's the formula. Notice that really it's the same formula that we had before. The margin of error is found by taking, and this is the one part that's different, aside from also this, but instead of using a z-value, we use something called a t-value. And it's the t-value for a given level of confidence. S is, instead of sigma, replaces that as an estimate of the population standard deviation, and we divide that, of course, by the square root of n as before. Once we've calculated error, then we create our confidence interval as we did before. We add the error to x bar and subtract it from x bar. This is a trilinear inequality notation, and then of course here we have the interval notation displaying the confidence interval. Let's talk a little bit about the t distribution. This is a different calculation than we have with z, and in fact the t curve itself differs from the z curve in many ways. But it also has a lot of similarities. The t-curve is symmetrical and bell-shaped, just like the normal curve. And it also is centered around 0, just like, of course, the standard normal curve as well. The one thing that makes it different is that the t-curve changes, the curve itself morphs, depending on its degrees of freedom, which we sometimes represent with df. We'll talk about that more here in a minute. The total area under the t-curve equals 1, and the x-axis is horizontal asymptote for the t-curve, just like with the standard normal curve. So you can see there's a lot of things that are similar. The one thing that's different is that the fact that with the standard normal curve, it never changes. It's always centered at 0 and has standard deviations of 1. The t-curve's shape, even though this also is centered around 0, and the standard deviation is 1, just as it is under the z-curve. But the area, the shape above the x-axis, does change depending on the degrees of freedom. Here's a picture of a couple of t-curves compared to the normal curve. The normal curve we have here is represented with the green curve. You can see that the other two curves are very much like the z-curve in nature. They're bell-shaped and symmetrical, and they're centered around 0. However, depending on the degrees of freedom, you can see here the blue one has a degree of freedom of 1. You have much fatter tails around the ends. And even when we change it slightly, and like I said, it changes with every change of the degree of freedom, we still end up with much fatter tails than what we have under the standard normal curve. This orange curve represents a degree of freedom of 6. Etc. The one parameter that we have is degrees of freedom, and as the number of degrees of freedom increases, you see the t distribution approaching the same properties as the standard normal distribution. Here's where I'd like you to, let's define what the degree of freedom is before I take you to the next slide. The degree of freedom is defined as being 1 minus the sample size. So degree of freedom is very closely tied to the sample size that you're pulling from the population. And we subtract 1 from it, just like we do when we calculate S, which is the standard deviation of a sample. So the main idea here is every time we increase our sample size, that in turn decreases or changes our degrees of freedom, and we get an entirely new curve above the x-axis. With a new curve, we get new areas. And so our t-table, which we're about to look at, looks very different than our z-table. in that every time our degree of freedom changes, we would have to get an entirely new, if it was laid out like the Z table, we'd have to get an entirely new table because the curve, therefore the areas are going to change um, as my sample size increases. Let's take a look at the t-distribution table so we can compare it to the z-table. Now the table that I have differs slightly, and I'm gonna exit out of here in a minute to go take a look at your table so we can go over specifically how this one is set up. The table that you have is actually the same table that the previous book that we used had. And it's probably one of the best things I like about the book. It's probably one of the only things I really liked about our previous book was the table. It's set up really nice and much easier to interpret than the one, most of the T-tables I've seen from other books. But let's point out some main things, and then I'll take us over to the other the book, or the other table. So in a t-table, the body of it is actually where we find our t-values. Contrasting that, of course, with the z-table where the z-values were along the sides of the top. So our body does not contain areas like it does under the z-table. The body actually contains our t-values. The side column contains our degrees of freedom. And the top is denoting, in this case, you would see that the top denotes the area to the right of a given t-value. So for example, this t-value here has 2.5% or 0.025 to its right. This has 1% to its right, and this has 0.5% to its right, etc., etc. And as you go down the table, you're going to notice that the t-values change as we increase our degrees of freedom. That's because the curve itself is changing, and hence what t-value would take to mark out 2.5% to its right changes as well. Let's take a look at your picture, which here's a picture of what you're hopefully looking at as well. You can see here along the sides we have our degrees of freedom, and then we also have along the top your confidence levels. The confidence levels correspond to a confidence interval. Okay, and what you want to keep in mind about this top column is that these are percentages for capturing that percent in the middle. So for example, this 0.95%, or 95%, sorry, for 15 degrees of freedom, the value that would capture 95% in the middle, like we would have for a confidence interval, where 2.5% is left in each tail, is 2.131. One thing I want you to note is that as our degrees of freedom increase, that these values begin to look more and more like the z-values. And at the very bottom of the curve, you can see actually that we have all the critical values for z listed as well. So as our sample size increases, my degrees of freedom increase, this value gets closer and closer to 1.96. In fact, after 1,000, you really can't tell a difference between the t-value and the z-value. The curve eventually becomes identical to the standard normal curve. But in the meantime, it does differ quite a bit. You can see that at 15 degrees of freedom, we have 2.131. That's a lot further out, standard deviation-wise, than it was under the standard normal curve, where we went to the left and to the right, 1.96. You'll also notice on this table that all the t-values are positive. That's because of the way that the t-table is set up. But because it shares the symmetry, as does the standard normal curve, if we're talking about a value that's on the left, we just have to stick a negative in front of it. Also, I'm going to point out here at the bottom that you have, and this is going to come more in handy in our next section, but you have one-sided P and two-sided P listed. Um, what this means is what the area would be in one tail. So for example, when we were looking at the 95%, that's 2.5% in one tail for a sum total of 5% for the two tails, which goes with a 95% in the middle, which is our confidence level. So when we're referring to confidence level in the context of a confidence interval, we can actually go straight to the top here, look at whatever level of confidence we're using for our confidence interval, and then go down to the number of degrees of freedom to find the critical value for that particular situation. All right, and you can see on my slide show here, we're going to find the value for a 95% level of confidence with 15 degrees of freedom. What would be the t-value that would go with that? So in this particular thing, this is the column that we would use for 15 degrees of freedom. We've got this row, and for a 95% level of confidence, that would be this value right here. This has 2.5. Remember, this is showing to the right of t, and so 2.5 would be in the tail. That would be the same as a 95% level of confidence. If we have 2.5 in each tail, that's 5%. That means there's 95% in the middle. So the table you have is a little more straightforward in terms of determining which column you should be in, because a lot of times people will get thrown off by that and they would go to this column instead. So using your table, how many degrees of freedom make t equal to 1.86 for a 95% confidence interval? Refer to your table, pause if needed. And looking in the body, which is where our t-values are found, we can see that it takes 8 degrees of freedom for t to be equal to 1.86 in the 90% confidence interval column. Secondly, find the value of t such that the shaded area is 0.10 in each tail for 17 degrees of freedom. Find the t such that the shaded area is 0.1 in each tail for 17 degrees of freedom. If we have 0.10 in each tail, that means we have an 80% level of confidence. Remember, one tail having 10%. In a confidence interval, we have two tails left over, and so that would be 10% in each tail, which would leave us 80% in the middle. So you should have gone to the 80% level of confidence column and gone down to 17 degrees of freedom to find t equal to 1.333. This would be our critical value of t. Find the value of t such that its area to its left is 0.05 for a t distribution. Assume 11 degrees of freedom. On your t-chart, since they're describing one tail, notice that it says the area to its left is 0.05. You can refer down to the very bottom where it says one-sided p, go over to 0.05, and you're going to see that you're in the 90% confidence level column. That's because, again, with 5% in one tail, that means 10% total in the tails, which would be a 90% confidence interval. And for 11 degrees of freedom, you should see a t-value of 1.796. Now, of course, we're taking the negative of that because we're assuming 5% in one tail to the left. So that would necessitate that we're to the left of 0, and we're looking at that left tail having 5% in it. So do be aware of what side you're on in terms of the t curve. All right, so let's look at creating a confidence interval when we don't know the standard deviation of the population. Notice that it doesn't mean that we don't know the standard deviation at all. It simply means we don't know the standard deviation of the overall population. What we do instead then is find the standard deviation of our sample and use that as an estimate, a point estimate of the standard deviation of the population. So a student records the repair cost for 20 randomly selected computers. A sample mean of $216.53 with a standard deviation of $15.86 are subsequently computed. Notice that the way that they describe the standard deviation is that it came from the sample. We calculated the mean from the sample and the standard deviation. That means 1586 is our S. And also, because we're dealing with a sample standard deviation, we need to use T instead of Z. Now we're going to determine the 98% confidence interval for the mean repair cost of all computers. So the first thing that we need to do is to figure out what our critical value is. In order to determine margin of error, we need to have a t-value for this level of confidence. Our confidence level is 98%, and we have a sample size of 20. With a sample size of 20, our degrees of freedom are 19. See if you can find the t-value for this confidence interval. Looking on your table, you should see 2.59539 as the given t-value for that level of confidence, 19 degrees of freedom. Our S value is $15.86, which we're going to divide by the square root of the sample. The result is 9. This, of course, we can interpret as being not just 9, but $9 specifically. And so we're going to take our sample mean. This really should be an X bar here and here. And we're going to take the sample mean, which is 216.53. We're going to subtract 9 from it and add 9 to it, which gives us our confidence interval going from $207.53 all the way up to $225.53. And so this is how we can word our conclusion. We can be 98% confident that the mean repair cost of computers in general, notice we're talking about the population, we're not talking about our sample. We already knew what the mean cost was for our sample. We're trying to apply this to the whole population. That the mean repair cost of all computers is somewhere between $207.53, $225.53. Now I would like you to create a confidence interval based on this data and to draw out a conclusion as well based on this data. You can go ahead and pause if you haven't. Here is the results. Now I do want to point out that using the table, this actually comes out slightly different than what I have here. I have it as $43.59. It really should be 61 cents and $46.39 on this end. So with our conclusions, we could say we can be 90% confident that the accountants spend on average between $43.61 and $46.39 a week on lunch. That concludes our introduction to T and creating confidence intervals when we don't know the sigma, which is the standard deviation of the population.